Supplemental math videos from Circle Christian School. Behold the mid-segment theorem. When you think about mid-segments, think about what the word says. Think mid, which is middle, and segment, which is a line. But see, these cute lines have some neat geometry properties. There are parallel things going on. They have half the size going on, and they make the original shape inside whatever polygon you happen to be dealing with. Reminds me a little bit of the Little Rascals, actually. I've got a pickle, you've got a pickle, your pickle's half of mine. Today I'm going to start with a right triangle. It's not necessary to be a right triangle to deal with mid-segments that happen inside of triangles, or actually any polygon. I'm just picking a right triangle. All the properties will end up being the same. So the first property that we're going to look at is that any shape, and that's going to be the pink shape, so triangle ABC, is my original triangle. Then taking a look at points D, E, and F, you'll see that, here, let me circle D, E, and F. D, E, and F are points that are mid-segments because, go ahead, because you were shown that the segments are cut in half. Because two segments are equal, then the point in the middle is the midpoint. Very good. So that's the first thing that we have, is that points D, E, and F are midpoints. So what we're going to do, or what happened, is that there were lines drawn from each of the midpoints. That's how mid-segments happen. They're lines drawn from each midpoint. Okay, here comes all the cool little properties. The first little property is that the original segment, or side of a polygon, in this case a right triangle, is always going to be parallel to the one inside. So what we have here is that line segment AC is parallel to line segment DF, and so forth for the other two sides. The next thing is that we're told that A to C equals 8 units. So I'm going to put a U there so that we know it's 8 units. That means that from A to E equals half of that, which is going to be 4 units, and E to C is half of that, and that's going to equal 4 units. Okay, so because that is 8, then we know that the line from D to F, the next cool thing that happens with mid segments, talking about the middle all the time, that's what the mid means, is also going to be half of the original, which is also going to be 4 units. And because it's 4 units, and AE is 4 units, and EC is 4 units, then by the transitive property, segment DF is also congruent to the other two segments. So therefore, it would be half the size. And it would happen with all the other relating sides. BC is going to be twice as much as the parallel line D to E. And A to B is going to be twice as much and parallel to E to F. So therefore, It's going to be congruent to those segments, and so forth as you go around here. Now what it does is it basically breaks up the larger piece into 4 similar, which means they're proportional to each other, triangles or polygons. So now we have 4 of them. So if the original perimeter of the triangle was 6 plus 6 plus 8, because that's what a perimeter does, the perimeter of triangle ABC would in turn equal 20 units. And because triangle DEF has sides that are all half as much, the perimeter would then equal half as much also, of 10 units, because over here would be 3, and the other side, since it was 6, would also be 3, and 3 plus 3 plus 4 is a grand total of 10. Likewise, the area now, if the area of the larger triangle is 1/2 the base times the height, and I'm going to tell you that this is a right triangle, then it would be 6 times 6. Then divided by 2, half the height. So the area would equal 18 units squared. And the smaller triangle on the inside and all the other smaller triangles on the inside would equal 3 times 3, then divided by 2, which would be 9 divided by 2, or go ahead, think. 9 divided by 2. Somebody out there is already yelling and telling me what it is. 9 divided by 2, 4.5. Oh my goodness. Craziness there. Okay. So looking at the relationship between the two areas here, you would see that the smaller triangle, which is 4.5, in relationship to the larger triangle 18, would equal 1/4 as much. So the area for any of these triangles is going to be 1/4 as much as the larger triangle, or in this case 4.5 units square. 1/4 of 18 is 4.5. All right, this is a rather special triangle, one that we call a Sierpinski triangle. Sierpinski was a rather famous mathematician that worked heavily in fractal geometry and some fractal algebra. In fact, this is a little bit where some of the complex numbers come from, and Mandelbrot set, just to throw out some fancy math words here. But generally, you start with any regular given shape, and what you're going to do is use a lot of different midpoints, which gives us mid-segments, and just keep breaking off into smaller little triangles. So what we're going to do is start with our 5 geometry strategies here, and we are going to work at solving. Well, the first geometry strategy is, of course, to draw. It's kind of a fun thing to draw, and if you get really fancy here, you can do some coloring in. The second geometry strategy is to, what are the givens and what are the finds? Very good. The third one is to do some labeling. Fortunately, a lot of the labeling's already done with us, which was taken care of up in the drawing, if what you did is you copy the picture. And now we're going to make our geometry strategies. Okay, looking at this regular triangle, an equilateral triangle here, we notice that each one of the sides here are being broken up totally in half. We have a midpoint here. And by virtue of having a midpoint here, we have the two sides that are congruent. We can also see that this has happened with all three sides here. So we have midpoints, and if we draw a line from midpoint to midpoint, we of course have mid-segments. So our geometry strategy is that we have several mid-segments leading us to some really cool mid-segment properties. And now we're going to replace the geometry property with the algebra. Noting that B2, and actually this was supposed to be D over here, so I'm just going to put a D over here, that BD is going to be parallel to EF here, that we notice that because of the properties, then these two are actually going to be congruent to each other. And that's how we're going to set up the math, that the first line segment, BD, is congruent to EF and also parallel. So we're just going to replace it with the algebra, 2x plus 3, and it's going to equal 21. And then we're just going to solve. Step 1, draw that little fence of equality there. We're going to isolate the variable and move the number over. All right. Now we're just going to do the math. Remember to do everything left to right. The whole thing was to cancel out those 3's from one side to another side. There's our little fence posts that go on the fence of equality. 21 take away 3 is 18. Now we still have to isolate the variable using the multiplicative inverse. Divide by 2, divide by 2. And x is going to equal 9. So if we plug it back in to the original equation, George Polya it, we would have the 2 times the 9 is 18 plus 3. That gives us 21. And everything's happy in the Sierpinski land of triangles. All right, here's a 50-point star maker. And if you remember, star points are awesome. And you want to make as many star points as possible. Here's a great way to start your new year off. We have a Sierpinski triangle here, and you're given that the large triangles area, that's the total one in yellow here, equals 20 square feet. What you need to do is find the area of the green triangle and then the combined area of all 3 red triangles. So that means this red triangle plus this red triangle plus this red triangle. All right, guys, have fun.